standards. And we have integrated this pipeline now into Galaxy. So it's a Galaxy-based workflow system for ease of use and scalability to other priority pathogens, which we are already doing. What you will see here right now are standards for AB, which is the most critical pathogen according to both the WHO priority pathogens list as well as the Indian priority pathogens list, right? And that is why we started working with AB. So this was available online. So what we have understood from today's discussion is that DNA sequencing is the new microscope, right? It was like almost 400 years since the invention of the light microscopy. We still use it in different contexts, but last 40 to 50 years since the invention of DNA sequencing, the technology has transformed biomedical research in ways we could never imagine. And it is beginning to transform clinical medicine. We have discussed today the advantages it offers. We also discussed the limitations it might have. But DNA sequencing will have a long impact, and it might exceed that of a microscope subsequently because there are limitations to the way the clinical data sets can be handled. And that is why, to give you an idea of how this can be done, we have selected an already existing Galaxy training network tutorial, which is antibiotic resistant detection. The reason we did that is the content of this particular exercise is already available online. And since it is available online, you already have the content there to go back and practice. And that is why we thought it's important that we share with you something where which there is a decent amount of information available. All right. Now, with that, I would like to hand it over back to Dr. Harpreet and Dr. Vipin to basically proceed with the demonstration. I'm available here to answer any questions you have so far. And in the meantime, so if there are any questions you would like to clarify at this stage, I'm here. And then we can start with Dr. Vipin's, the session of demonstrating how antibiotic resistant genes can be identified using genome sequence datasets generated through nanopore. So are there any questions? All right.
Thank you, Professor Anshu. Am I audible now?
Yes.
Just give me a minute. I'm not able to hear your voice.
Okay.
Okay, fine. So I think it was an excellent overview by Professor Anshu for antimicrobial resistance genes and pathway and how it is important. And I was really excited to see some of the experiments, like the experiment with a very large petri plate with the 4 feet into 2 feet. It was really something amazing to know about that. And now it's really fine that we have a data, and also she has also given overview of some of the resources which we can use to do the analysis of data, because getting a metagenomic data is one aspect. But the second aspect is how to analyze the data and how to get something out of data, how to derive knowledge from data, and that's where bioinformatics play an important role. Yeah, and so I will be happy if you have some questions from the audience. Yeah, so the floor is open for question. Anyone can type the question or raise his hand so that we can continue the process.
Looks like the people are not happy with Q&A's method. Maybe the chat I will enable it again.
Yeah. You can enable the chat. I think
until Kiran enables, I will ask one question to Professor Sararaj.
Yes.
This is a question of experimentalist to me. In silico identification we do, and then the experimentalist asks, how best your prediction is and the probability of prediction, how do we ensure that which prediction predicted the examples we need to take ahead and do the experiments? Do you have any answers to that question? How best optimize and then interact with the experimentalists to give them the proper examples for them to do further experimentation?
Right. So that's a very valid question, Dr. Jayaraman. This has been a major limitation in, translating predictions to an experimental validation status. So the way I see, and we have done it in few cases now, it might work is that if we stop using our machine learning based methods or our statistical methods as black boxes, if we can explain why the method is able to identify and predict a specific property in context of the biological mechanism, that becomes a very convincing way to basically identify and talk to the experimental community, to convince them to actually go ahead and validate some of the predictions. Now this has worked with me at least in 2 or 3 different cases personally. So the minute you say I predicted this, and this is a prioritization, it's a ranking, we can start with 1, 2, 3, 4. And so that ranking is important because now you are laying emphasis on some of the predictions more than the understand why that ranking in biological mechanistic context. And that is a very convincing argument. Now I have at least 3 experimental groups working, in collaboration with us to verify what we predicted. And that worked as a good argument. The minute we start explaining what we have seen and there is no explanation, it gets extremely difficult to convince. And that is when we need to understand the questions we are asking even better. And that is the reason today when I was, for the workshop itself, it's important for the participants to understand the context and the background, and then apply that knowledge onto doing the analysis. Minus the background doing analysis and not explaining what we actually see, it can be a strong deterrent to take it downstream. That is what I think.
Thanks a lot, Madam.
So there is a question by Priyadarshini N. In case of no reference genome database or de novo analysis, how can we build a reference database in Galaxy? All right. So I would. So when you say reference, Priyadarshini, why do you need a reference database here? Because see, if you look at some of the methods that I told you, we normally use reference databases mostly for assembly, right? And there are methods to do both de novo assembly as well as reference based assembly, and tools for both are available in Galaxy. So if that is what you're asking, you actually have applications, and I'm pretty sure in the next keynote by Gareth, he will take you through the NGS thing, and in Vipin's talk also, he will cover components of assembly with Nanocore. Yeah, but you can do that with Galaxy. You can do both de novo and reference based. Taxonomic assignment using meta. What are the things need to be looked out to find the. Okay, so the catch here is, Nandan, that you need to understand what level of resolution is fine with you. Like say for example, in most metagenomic sequencing, the preferred thing is to do 16S. You really don't do a whole genome, right? But then there are papers who have clearly highlighted the limitations of 16S based readout in delineating certain strains, so it actually differs from strain to strain. Some genomes are very conserved. You may not find that much variation. They don't do a lot of horizontal gene transfer. Things are easy. The other genomes, on the other hand, undergo extreme amount of horizontal gene transfer. Doing only 16S may not really help you understand how that strain evolved. So you then need to look at a whole genome sequence. So it really depends on the question that you are asking, and there are very clear-cut guidelines in terms of saying how do you define a new species, how do you define a new strain, When do you bundle the species together into as a single species? But the point is, if you talk to people who do molecular taxonomy, there is a lot of discrepancy in the community, and the reason being very simple, that different cutoffs will apply to different microbes. So the minute you start applying an umbrella cutoff value to your entire metagenomic data set is when the problem seeps in. So you need to understand the question you are asking and then categorize that in terms of which species are you more interested in looking at. So it's not one size fit all kind of a thing. You need to be, people are realizing that there are a lot of papers this year that came out on metagenomic sequencing and the challenges with using only 16S. So you need to look at whole genomes.
Thank you, Dr. Anshub. We will still wait for some questions because I think your talk was on metagenomics, and so people are preparing some meta questions for you. So just wait. So that's why we are taking time.
Not a problem. We can also start with the Vipin's presentation and then we can take questions in
Yes.
between, because I think he'll have some of the demonstrations and then we can keep looking at the chat window for more questions.
Yes, I think that's an excellent idea because sometimes while going through the demonstration, you connect to the biology. So really an excellent idea. And I welcome Dr. Vipin here. Good morning, Dr. Vipin.
Good morning, Dr. Rafi. Thank you
So
for that.
I'm audible, and I think your voice is also fine. So all the participants, please ready for the next talk. I think that's very biological background is very important, which Dr. Anshu has given in a very nice manner. So now let's move on to how actually we try to analyze the data. That will be the second part of this talk, this particular session. I think not talk per session. So for that we have with us Dr. Vipin, and it's my privilege to have a brief introduction for Dr. Vipin. Dr. Vipin Singh is working as an associate professor in biotechnology at Chandigarh University in Punjab. He has also served as assistant professor at MIT University, Noida. He has been a postdoctoral fellow at IBENS Paris from 2019-20. Uh, he obtained his PhD from CSR CCMB Hyderabad. I think both of them, Dr. Anshu and Dr. Vipin, are the product of CCMB Hyderabad, and you can sense upon the importance of the intellectual properties they have. He has over 10 years of teaching and research experience in some of the best private universities in India. His specialization is in genomics, transposon, bioinformatics. He is proficient in many programming languages, including Perl, Python, R, Awk. And beside teaching and research, he has many extra co-curricular activities in his bag. For example, he successfully working as a placement coordinator at Corporate Resources Center, and also as an admission coordinator at the admission cell in his university. He has been instrumental in grooming students through soft skill training sessions and placing students in various biotech and allied companies. So I think students can even ask some questions related to the placements to him. And he has been extensively using social media and other platforms to prepare his students for NetGate fellowships, online classes via Google, and I think he was well prepared for the online classes before the pandemic began. So and apart from these things, he has been an excellent researcher, and he has published many papers in international journals of international repute. And I think we will be mesmerized with his talk today, particularly demonstrating the things how we can deal with antimicrobial resistant genes using different bioinformatics tools, pipelines, and analysis workflows. So on behalf of the entire organizing committee, on behalf of BioNews and INBIX pre-conference committee, I welcome Professor Vipin Singh to this platform, and I will request him to deliver his talk. Thank you, sir.
Thank you, Dr. Hardik, for your kind introduction, and it puts me under a lot of pressure to perform.
Sorry to interrupt. Sorry to interrupt, Dr. Vipin.
Yeah,
Yes,
yeah.
Yeah, just one couple of instructions I wanted to give because it's going to be a practical one.
yes.
Okay,
So,
okay.
yeah. I hope all are already registered to your galaxies, and also not just registering, but please do visit the link which I'm also providing here in the chat, but it's already provided in the instruction website link which I initially gave. Once you once you register your account in the galaxies, do please visit this uh, link which I gave in the chat right now, so that you will be in the special queue whenever you do any jobs for the present workshop sessions. Your jobs will be on a priority basis. Thank you.
All right, so let me share my PPT and give you a brief introduction to what we're doing. So background is important and biological context is important. So let me just take you through my presentation, and I'll share my entire screen, and then of course here you are, share, and let me just open the PPT now. So here you are. I hope you can see my presentation now, right? Right? Can you see the presentation?
Yes.
Can you just? Oh, great. Oh, great. So first of all, thank you INBIX, and thank you everyone for inviting me here. And then of course let me start the presentation. So what we're going to do is to look at antibiotic resistance detection using Galaxy. And we'll use a specific paper that has been mentioned in some of the data reference, and then we'll pick up the data from there and go forward. Some of the jobs will be time taking, so you may not be able to parallelly do it. So, but of course, I have taken the screenshots of everything so that I will be able to follow up. And or you can do it immediately after the workshop, or maybe towards the end of the workshop, right? So we'll go around with this. So antibiotic resistance detection with Galaxy, we first start with some basics here. So we're talking about sequencing, and today, of course, everything starts with as I'm sure pointed out. Sequencing is the new microscope. So what is sequencing? Sequencing is to determine the order of nucleotides in a given DNA molecule. It could be your whole genome, it could be a plasmid, it could be many things, and it could give you a lot of information in terms of what genes are present, whether your plasmid carries your antibiotic resistant genes or not, which is the exercise that we're going to do today, right? So then all of you are sure genome is one of the genetic material in an organism or cell. And sequencing genomes is challenging. Why it is challenging is right? And that would be the tone for why certain tools are available for assembling and other things. So we move on and talk about this now. So why do we want to sequence genomes? Of course, one is we want to know what is the genetic code that we have in terms of the genetic letters that we have. So we want to understand the basic composition of human and other genomes. We want to identify variations that exist between humans or between different strains of microbes and so on and so forth. And we also want to especially identify variations with respect to the diseases, right? So why are some humans more susceptible to disease? Why are some not susceptible? Why do certain viruses or certain microbes cause disease? Some are non-pathogenic and so on and so forth. So those kind of things can be illustrated when you know the actual DNA content in terms of nucleotides, right? So that is where the code is. So why not get into the code exactly and move forward? So here is our story, and this is where the sequencing had begun slightly earlier than this, but in 2001, first human genome was sequenced, right? And the first draft of human genome was made public. It was announced by the then President of the United States, and it was there were two efforts, one by the government, which is Human Genome Project, and also its own genome released its own genome of individual, right? So this is in February 2001, and that is also the start of what is known as next generation sequencing, because people realize that if you want to go into personal genomics and sequence personal genomes, Sanger sequencing technology, which was until then the sequencing technology, is not going to be enough, because with Sanger sequencing, it had taken us 10 years and around $3.2 billion to sequence the first genome. So that is where the start of next generation sequencing or high throughput sequencing began, right? And that is the basic story that we have. And then, of course, let me also put it in context. So let's say you have an image here, and this image of fiber type is. And let's say I want to break the symbol into several parts and then reassemble. So I'm breaking into 4 parts, 9 parts, and 56 parts. So one thing is I want to ask you which of these parts will be most easy to assemble, A, B, or C. Right. So it is very obvious that C would be most difficult to assemble. B with 9 parts will be relatively easier, and A with 4 parts will be very easy to assemble, and you cannot go wrong here. In this case, where you have smaller fragments, you may be able to, sometimes because this fragment and this fragment may look very similar, you could actually be putting up this one here and this one here, and it would be a fault in the actual assembly of the photograph, right? And the same happens with the genomes. Uh, because we do not have a technology that can directly sequence the entire genome, we break it into parts and sequence. And depending on what is the length of the parts, you may have an assembly that may be more faulty and that may be less faulty. So here you are. This is basically, this picture represents your genome, right? Or let's say a plasmid sequence, a large plasmid sequence, let's say a 100 kb plasmid sequence. So this is your genome. These where you have big parts of your photograph, these would represent long reads, or you have broken your genome into longer parts and you're directly sequencing those parts. This one would be intermediate reads, where we have smaller fragments, but not so small as the last part here, which is your short reads. So currently, when you talk of sequencer, there are two categories of sequencers that we have. We have long read sequencers and then we have short sequencers. Right? Each one has its own advantage and disadvantage, and we'll come to it as we talk about it. And the exercise that we do will be based on the nanopore sequencing data, which is the long read sequence. So here is the important part here. So read length is extremely critical to assembly of the genome, whether you're doing a reference assembly or you're doing a de novo assembly. So what is a reference assembly? I have this picture in front of me and I'm assembling the fragments based on what is available in the picture here. So it gets a lot easier to assemble. De novo assembly essentially means that I have moved the parts and I have to figure out what my final picture is going to be. Right? So that is something that you have here. So read length is the maximum sequence length that can be obtained in one sequencing reaction, and this is specific to each sequencing technique. And based on this, you have long read sequencers and short read sequencers. And we'll come to it in a short while. We'll talk more about it, and we'll specifically talk about nanopore, which is a long read sequencer. And then as I said, depending on what is the read length, it is a critical parameter for correct assembly of your fragments or the entire genome that you want to actually get the assembly for. Right. So let's look at the steps in sequencing a genome or a large DNA piece here. So here is what you do. Let's say this is our genome here, because there is no technology that can directly sequence from one end of this DNA to the last end of DNA, you have to break it into parts. So we break it into parts. So these are our parts here, and individually sequence each of these parts. Now, depending on which sequencing technology you use, you will have either long reads or the sequence coming from these parts, or you will have short reads. Right? And we'll talk more about that as we move along. Now, since you have fragmented it, the final challenge is to assemble it back in the order they were in the original DNA sequence. That part is known as assembly. Right? So, for sequencing a genome or a large DNA piece, a genomic library, there's another library essentially means you're breaking the genomic DNA into smaller pieces. Then you sequence individual fragments here. The fragments are very reads are, you get the reads from it, which is the actual sequence of individual parts, and then you assemble it together in the order they were in the original genome, so as to get the final sequence of this piece of DNA. Right? So that is the story behind sequencing, and that is where the long read, short read story comes in, because if the shorter the fragments, the more difficult it is to assemble into the original full DNA. Right? And the longer the parts you will have first, if you are making it longer fragments, you will have a smaller number of fragments to assemble, and then of course what is also important is that since you have a smaller number of fragments and can read a longer sequence, the assembly becomes a lot easier as compared to what you have otherwise. And one important here also is the reads that you have. So this is what we do. You finally assemble your sequence and get the final sequence here. So here is another problem. Let's say this is a plasmid that you want to sequence, and this plasmid has, this green ones are your unique sequences, and the red ones are your repeat sequences. So as the name indicates, repeat means it is the same sequence coming multiple times in your DNA that you want to sequence. So let's say you have fragmented it and you have sequenced individual parts, and it so happens that this A fragment and C fragment, they have unique ends and they overlap with each other. So it is very easy to identify that C follows A. But when you come to C, C is ending in a repeat, and B fragment is starting with a repeat. Likewise, E is starting with the same repeat, and F is also starting with the same repeat. So now it becomes a problem to identify what comes after C, because both B, E, and F have the same starting fragment, and which is overlapping with the end of C. Right? I can't see the chat. Maybe I'll just escape and see the, because I can hear somebody is pinging or something. So is it okay that I continue, class? Everybody following?
Yes, please, you can follow.
Okay, so then we move on, and so here you are. The problem with assembly is that while it is clear there is unique overlap between A and C, and this overlap is not found in any other fragment, so you know C is coming next to A. But after C, whether B is there or E is there or F is there, becomes a problem, right? And this is even more a problem when you're looking at smaller reads. Smaller reads have very small ends, and they're likely to be ending in repeats, and therefore beyond that, assembling becomes a problem. And even if you go for eukaryotes and higher genomes, if you talk of human genome has more than 50% repeat sequence. So therefore, one of the major stumbling blocks while sequencing the genome and doing a renal assembly of the human genome for 10 years was majorly because there were so many repeats and there was no reference that were available at that point of time, right? The other strategy that when you do never assembly, you start from scratch and do self-alignment and see where are overlaps, and then you get your final assembly. This assembly is tedious, but it is likely to be, and it may also be error prone because of the repeats that are present. The other way that you can do it is a reference-based assembly. You already have a sequence genome, you align your reads that you get. But the problem with reference-based, you will not get novelty because you're only aligning to what is known before, right? So therefore, both assemblies have their own pluses and minuses. And the idea of getting a problem is improved when you have longer reads, because then the assembly, the fragments will are less, and therefore the chances of going to an error region are less. Also, when you have longer reads, they are likely to be covering the entire repeat sequence, right? And that allows you to basically have unique ends, and that allows you again to assemble more properly. And therefore, now what we're preferring is a long-range sequencer. Now, the problem with long-range sequencers is that they are usually, if you talk of individual nucleotides there, they are usually more error-prone than short-read sequencers. So what we now move on is what is known as a hybrid assembly thing. So you specifically do part sequencing with small read sequencers and part sequencing with long read sequencers. Long read sequencers and long reads will give you the context, and small reads will give you the precision that you want. So currently, if you look at the sequencing technologies, there are contemporary sequencing technologies. Of course, Sanger is obsolete now, more or less obsolete. Sequencing was one of the technologies that was available, which has also become obsolete. Currently, if you look at the sequencers, there are 4 major technologies available and can be clearly classified into short-read sequencers and long-read sequencers. So virtual computer sequencing, or Illumina, which is the most successful and commercially most successful sequencing technology, is a short-read sequencer. You can have reads up to 150 to 200 bases, and there is an effort to improve the read length, but for now it gives you very short reads of 150 to 200 bases. Iron Torrent by Roche again is a short read sequencer. It gives you a read of around 100 bases. Nanopore and single molecule sequencing by Bio, and Nanopore is from Oxford. Oxford sequencing. So these are long read sequencers. They can give you sequences very easily. Up to a read length of 10 kb, 20 kb, 30 kb, 40 kb, and even beyond. Right? So this is now our major sequencing technology where we are heading to, and people are trying to reduce the errors that come in with these technologies. But for now, Illumina is the market leader, but the movement is towards long read sequencers. So, nanopore is very simple, and if you see, the idea is very simple. You have a nanopore, this is the pore of nano dimensions, and basically which is put across an electric field, so there is a certain amount of current that can flow through it. And then, based on the obstruction that you produce here, you will have characteristic fluctuations in current, and those can be a readout for what is the molecule you are trying to push into this nanopore here, right? So this is, let's say, this is based on the stereochemistry and based on the size of the molecule, there will be characteristic fluctuations in current, and that amperometric output readout that I get is basically an indicator of what molecule is passing through. And fortunately for us, when you pass the DNA through it, the fluctuations that are produced by A, T, G, and C are different, and therefore a direct readout of what nucleotide is passing through the nanopore can be obtained. Right? And what is also important in nanopore is that even a methylated cytosine produces a different fluctuation than a normal cytosine. So even a methylome can be read more easily in case of nanopore sequencer as compared to what you have in Illumina. Illumina, you have to do bisulfite sequencing for that. So here is a typical nanopore. This is the example here. This is a basic mechanism of how this thing is done. You use helicase to unwind your DNA, and then you push one strand through the nanopore. As the strand moves in, depending on what nucleotide is passing through the nanopore, correct fluctuations are reduced, and these fluctuations result in your indirect readout of the nucleotide that is passing through it. And the time of the sequence in the genome can be anywhere between the 20 minutes or larger size of sequencer is important because why nanopore is becoming a technique of choice, because this can be used as a point of care device. It is roughly the size of a pen drive, and you can carry it in your pocket and just plug into a laptop, and that is all you require. No extensive power usage or UPS or anything is required. So therefore, nanopore is a very promising technology here. The other technology is single molecule real-time sequencing. As the name indicates, you are using single molecule, and what you do is basically to increase the signal intensity, you reduce the volume in which the reaction is happening. So if you have the same bulb, let's say a 40-watt bulb in a larger room, in a medium room, and a smaller room will be more well lit. So you can basically effectively rule out the background and see the fluorescence. And to reduce the the misread that you have, or the fidelity of polymerase fidelity, or the misinterpretation of nucleotides that you may have, you basically circularize your DNA that you want to sequence, and sequence it multiple times. So here is your DNA polymerase, and it moves around, and basically you have your DNTPs that are fluorescently labeled, and that allows for multiple incorporation, and based on the fluorescence that you get, you are able to identify which nucleotide is there. Then you align this DNA that you get, and because this is the same molecule sequenced multiple times, when you align it, you will get each position, and you look for what is the nucleotide that is coming the maximum times. That is like a consensus sequence, and that gives you almost around 99% accuracy, is what is claimed by the company here. Right? So this is what you have, and the volume in which you do your reaction is what is known as zero mode wave guide. So here is your zero mode wave guide here, and this is you have your DNA polymerase immobilized into it, and you have a single template that is there. As the DNA polymerase moves through it, it incorporates the complementary nucleotides, which are differentially labeled, and therefore you can look at the fluorescence and identify which nucleotide got incorporated. And this gives you very high read lengths. Half of the data, if you see here in this experiment, is greater than 30 kb. Top 5% of the reads are greater than 50 kb, and some reads can be as high as 90 kb. And so basically, on an average, you could get 10 to 15 kb very easily. So this is the whole idea of sequencing here. And we are looking into the data that is coming from Oxford nanopores. So we are looking at nanopore technology data here. And this is just a size comparison. This is your sequencer. This is the long sequencer again. This is the MinION, which is your Oxford nanopore sequencer. It is the size of a pen drive, easily plugged into a laptop, and you can. This is your Illumina and torrent, and of course with due respect to history. This is your Sanger. This is where it began. Of course, Magnum will be also there, but it won't be automated. Sanger is where the actual sequencing story begins. And of course, whatever we have today is basically mostly derived through this. So this is a reference paper that will be used for our hands-on today. So if you see, this is published in Giga Science. This is a 2018 paper. The title is Efficient Generation of Complete Uses of MDR and Plasmids by Rapid Assembly of MinION barcoding sequencing. And so basically what they've done is they have sequenced plasmids coming from different strains of E. coli and other strains, and then they are looking at whether these plasmids contain determinants for AMR or not. So that is what we're trying to do, right? Okay. So let me move the Google Meet banner here so that we don't see. Okay, so I got some message that the banner is hiding the title, so I'm just moving it here. And the data for this is available here at zenodo.org, record 32475454504 and hashtag whatever, right? So this is your the site from where you can pick up the data and do your exercise. Some of these steps will be time taking and you may not be able to do it as we move along because of the 1 hour, roughly 1.5 hours to do this. But of course, you can do it at a later time. And I'll also give the reference. This is basically from the Galaxy tutorials itself that I picked up this exercise for you, so that your transition into Galaxy is easy and comfortable. Right? So what does this paper deal with? Let me just take you forward again. So basically, the paper is about identifying multi-drug resistance genes in plasmids, and one of the major ways by which multi-drug resistant genes can move into different microorganisms is via plasmids and via horizontal transfers. So MDR encoding plasmids are now considered a major vector that facilitates AMR transmission or antimicrobial resistance transmission among bacteria via horizontal transfer. And the idea is that while you could sequence it with other technologies, presence of insertion sequences like hash elements and other repetitive elements make the assembly very difficult. And therefore, a short read assembly is not a very perfect assembly. And if it is not a perfect assembly, the detections you make from that assembly may not be correct. So therefore, what people are trying to now is do, and what this paper shows is that you could use Oxford nanopore for and generate long reads, and those long reads can help you assemble the plasmid correctly. And once the plasmid is assembled precisely, then of course you are able to make your predictions on whether it carries the resistance genes or not. So single molecule real-time sequencing can also be used, but it is slightly more costly and has a very tedious library preparation procedure. And therefore, these guys prefer to use benign nanopore sequencing platform. And this is where we'll get the reads from. These are the plasmids they have sequenced. So they see a number of the plasmids RB01 to RB12, and they are coming from E. coli, Vibrio, Salmonella, and Klebsiella. And you have these plasmid profiles 150 kb, 100 kb, and this has multiple plasmids of different sizes. You can refer to the reference paper. If you so basic idea is if you want to really understand what to do going through here, first thing is you will have to read this paper, and then of course it will be more comfortable to you to do the hands-on, and you will also understand why we are moving on with this. So here we are, and these are the results that you see. So if you see RB01, it shows 8 resistance genes in its sequence, and the sequence is assembled using various softwares. The software that the paper has used, we are not going to use those softwares. We're going to use what is available in Galaxy for an assembly of the sequence. So let's move on and we talk a bit about where you can go for a reference in case you get stuck and you're doing it post the workshop. So this is the if you go to Google and type antibiotic resistance detection Galaxy, it will take you to this page here where every step of this exercise is mentioned very nicely by Willem de Koning and Saskia Hiltman. And you can also ask for help in case you get stuck with the exercise. So this is a tutorial from Galaxy itself, and we're picking up data from the papers that I mentioned, and of course we're moving on and we do the exercise now. And this is the URL for this. You can go here and do your and basically pick up your training and the guide for doing the hands-on from here as well. And the data is mentioned here from Zenodo. You can get the data using this link. So here you are. This is your Galaxy homepage, and we go to usegalaxy.org. It will ask you to create an account. I think I've already told you to create an account. You want to do hands-on. So you should be having an account. You don't have a very small step you can create an account. This will be the default page of Galaxy, and you will have James P. Taylor Foundation for Science and some fellowships in his name. So if you have not used Galaxy earlier, you'll not have nothing. You'll have nothing in your history. If you've used earlier, there will be a plus sign here that will ask you to create a new history. Right. So we move on and we come to here. So this is the first step here. You first create your history here. So you click on plus. When you click on plus, it will ask you to name your history. I've named it as INBIX-2021. right? And you can also name your history the way you want, and of course in the way you can remember what exercise you're doing here. So this is INBIX 2021. This is currently empty. I've not done anything here, and now I'll start with uploading my data here. So first, of course, is click on the plus sign and create a new history. If you don't have a history earlier, there will be no plus sign. You can directly name your history here directly and start with the exercise. Then the second important thing is you name your history. You can give a choice. And third, we come to uploading the data. So data uploading can be done through local system. If you have your files in local system, you can that way. Or if you have files directly, if you want to directly download files from GitHub or other places, Zenodo and all, you can do that as well. When you click on upload data, it will give you a menu. And here in this menu, I go to paste and fetch data because I'm directly downloading the data from the Zenodo site here. So I'm uploading two files here, rb01.fasta and rb02.fasta. And let me know if you are going too fast because some of you may be starting to do your hands-on as well. So in case you feel that you're going too fast, you can let me know and we can wait for you to be at par, right? And of course, I'll make the PPT available for you so you can use it to exercise when you have your free time and you have a good internet connection and otherwise. And it is always difficult to unless you have two screens, it is slightly difficult. So therefore, I have all the screenshots. I see some messages coming, but I'm on my PPT and I can't see the messages. So can anybody let me know a bit, or maybe I can just for a moment come back here, right? And see the chat as well. Right? Here you are, and I come. All right. So the links are being okay. So Dr. Harpreet, okay. So very good. So everything is here, and you can use that. So let me just get started again, and we will move on, and I'll show you some brief of how to go about it, and also the screenshots of the exercise that I have done, and then you can follow parallelly or at a later time, right? And that would be easier for you to do. All right. So here you are. I hope you can see my screen now, right? Okay. So this is your link location. So copy the link location, open the Galaxy Upload Manager. Let me just take my laser here. Open the Galaxy Upload Manager. So you'll say upload data, it will open the Galaxy Upload Manager. You select paste and fetch data. Paste the link in the text field and as a result out of the window. By default, Galaxy uses the URL as the name. So rename the files with the more useful name if you require. Right? So that is something that you need to understand. Then we move on, and now that we have the data, so if you see here, it is showing me two files. RB02 RB01. So these files are now uploaded in my history, and because all the steps that I do downstream will be same on both the files, what I would want to do is to bring them together into a single collection of data. So the next point is to make a collection of data, right? So here you are, we have fetched your data and everything. So now what I do is I check on this sign here, operations on multiple data sets, right? So I check this sign and I see my files here, and these will be checkable now. Once you check this, these should be checkable. I then select for, sorry, this is coming up here. So I check for operations on multiple data sets, and then I select the data set that I want to include in my final data. So what I'm doing is I'm combining these files into a single folder, so that every operation that I do downstream in Galaxy would be operated on both these files. I could give individual files one by one, but because it is the same operation on both the files, so I would want to club them together into one single folder, and that is how it works out. So I'll select these RB01 and RB02.fasta. So you know this is the FASTA file now because it is in .fasta, and of course I'll show the format as well, and we'll come back here. And then I click here for all selected, and when you click on for all selected, you will have a build dataset list option. So you click on build dataset list. When you click on build dataset list, you will have an option for naming your dataset. Right? So if you go to the next screenshot, you'll be able to see that, and let me pull this down again. Okay, right. So this is when you say build dataset, it will be able to it will take you to the next point here, and you click on this, and it takes you to the next point where it opens up a menu. And again, if you have selected the wrong files, you can discard here. If you want to keep all the files that you selected, you can keep them and give a name to your collection. So I give it the collection name that I give is plasmids, and this is again so a simple name for, because I know this is a plasmid sequence, I give it a plasmid name. So again, if you move on, I give it the name plasmid. And now if you see, I have my plasmid collection. There's a list two items, right? So next time, whenever I have an operation on both the files, I can simply select the plasmid, and then it will perform the same operation on both the files, right? So that is something that is again a lot more comfortable, and Galaxy puts you in front of clubbing data together for all the files that we operated with the same tool. You can club them together. So now we have done our basic data uploading, and we have clubbed them together in series or plasmid. Now we move on and we talk about the first thing. First thing, of course, is do a bit of data quality control, and we want to look at what is the data that we have, and basically also we want to see what is the average reading that we have, what is the mean reading that we have. Also, if you want to do some operation on your data, that can also be done. Let's say you notice that your initial sequence data is slightly error prone, so you would want to trim left first, then right, so right. So that can also be done. So we'll go by default option, not on the specific operation, but we'll just go by default, and we will see what is the output of the nanoplot. So this is the first exercise we're doing. We have uploaded the data, and we have clubbed them together into a single folder called plasmid. Right? So every operation that you do, you select plasmid, it will operate on both the files and give you again individual output for both the files. So here you are. We are now using nanoplot. Nanoplot is a various reports data, and the alignment. Right? It is part of the nano tool suite for visualizing the processing long read sequencing. And if here I search for nanoplot, and this is nanoplot here in the tool shed. This is your Galaxy tool shed. This is the part where your history will represent what all steps you have done. And this part here we can select for whatever tools. So I search for nanoplot, and it says plotting for nanoplot data and align, right? And then of course, as we move forward, we will select nanoplot, and when you click on this, it will then open up a menu for submission of files. So I click on this, and then it opens up a menu for submission of files. So here we are, and you have to because we're putting our operation in two different files. We'll select mode here. The file type that we have is fast. We are not having the files to files. The files. And if you go back to your slide, in from order was premature. So this is your RB01.FASTA file, typically a FASTA format sequence. We have the def line, and then you have the sequence followed by another. So this is a multi-FASTA file that we have, and this is what we're using here. So coming back here, we choose the batch format because we are doing the operation on two different files. Then, of course, the type of files to work on is FASTA, and then here you can give your dataset collection. If you want to give your individual files, you can click on this single file menu. If you want to give a collection, we remember we made a plasmid collection, right? In plasmid collection, we have two items, RB02 and RB01. So we'll click on this and we'll submit the data selection here. So I click this here, and so this is the batch, and then I click on the data selection, and then we choose this plasmid data selection. Right now in my instance, there is only one data selection, so it is very easy to do. So I choose plasmid data selection, and then of course I leave other options as default because this is a matter of experimentation. As you exercise more and as you are more familiar with nanoplot data, you will be able to identify which parameters to toggle with. So that is a matter of depending on how directly you're dealing with the data, you'll be able to understand what parameters to use. For now, the purpose is to give you a basic hands-on to move on, and of course, how far you trade is up to your requirements and your choice. So then we move on again, and we talk more about it. So you give a plasmid, and you can say execute now. So when you say execute, it will show you the job running, and then of course once the job is run, you have the files here. So nanoplot and collection 3, histogram read length is one. Then you have a transform histogram read length. Then you have stats post filtering. You have stats nano stats, and then you have a HTML report as well. HTML would open in a browser, and other reports you can actually visualize here as well. So we'll now move on and see one of these reports, which is your histogram read length report. So when you click on this, it will give you an option of whether you want to view or not. So let's move on, and I hope I'm keeping the pace fine. Anybody who has a problem, or maybe the organizers can tell me how is it going, right?
No, everything is going well.
Thank you, Dr. Adi. So that's nice to hear because there's a limited time. So I thought I'll keep screenshots, which will be handy for users when they go back and do it themselves. And some of you all may obviously be familiar and maybe a bit quicker on this. So coming back here, and now I go for nano protein telemetry, and looking at this data now, which is now on my screen, means the job is executed and the file is available here. So I click on this, and this is your menu here. You can directly save the file that is generated on your hard disk. You could generate a link here, this is for help or the query, and you could read the job, you refresh this, and this one is for visualize this data. So I'm visualizing the data here. I click on this, and then of course you get an image in PNG format, and when you click on this is what you get. So this is the histogram of read length, and you can see this is the number of reads that are available, and you can see more than 2,000 reads are somewhere around. This will be around 5,000 base pairs. This is 20,000, around 5,000 or 6,000. So we have some number of long range reads, and this is the general summary. If you look at the other file, the text database, you can also visualize something here. So if you see here, mean read length is around 4906.3, which is around 5 kbs. Mean read length, median read length is around 3.25. Number of that you have is 10,026 reads there here in RB01. And I'm looking at RB01 data. If you click on RB02, you'll be able to see the RB01, RB02 data here. And then the read length N50, which is basically 50% of the reads are just about these lengths, is 6473. So this is your basic stats of nano of the sequencing data that you put up for RB01 file. You could generate it for RB02, and there is another plot that's more complex, which we're not doing today. That would give you an idea of the quality of reads. Right? Then we move on and we talk more about, so this is the histogram, this is the summary, you can parallelly see here. Then we move on, and now what we want to do is, because we have fragmented our library, and we have long sequences, but these are not assembled together. First thing for our assembly is to do a pairwise alignment, all against all comparisons, to see whether they have unique overlaps, and if they have overlaps, what is the region where they're overlapping. So this can be done with a tool. The second tool in the tool sheet that we're going to use is Minimap, right? So this is for pairwise alignment and all against all alignment, and this is the major time-taking process that you have, because as you see, there are 10,023 reads, and each read has to be mapped to all remaining 10,022 reads, and that has to be done for every single read. So you can understand the volume of the effort that goes into, and the memory space and the time that will be taken for the algorithm to do this, right? So this is the major rate limiting step. Other steps are not so slow. So here you are. What is Minimap? Minimap 2 is a mapper. This is a new mapper, Minimap, and de novo assembler. So basically Minimap and the assembler, which is called mini assembler, they go hand in hand, and basically the output of Minimap is taken up by mini ASM for assembly. So Minimap, which is a de novo assembler, and a de novo assembler, that is mini ASM, for efficiently mapping and assembling smart or single molecule real-time sequencing data, or nanotechnology reads without an error correction stage. They can assemble a sequencing plan or medical data into a single kind of few minutes, and a 45x coverage of similar C elegance data can be assembled in 9 minutes. This is orders of magnitude faster than the existing pipeline. The Minimap 2 mini-SM pipeline is incredibly fast and memory efficient way of assembling long-read data. Mini-SM outputs unities and not quantities. So when you do the assembly finally, it will output what is known as unities. Unities are more confident quantities. And therefore, because it is not taking into consideration the context that it is doubtful, sometimes you will have a fragmented assembly. You will not be able to assemble the complete plasmid in this case, right? So, and we'll look at an alternate method that's known as unicycler that will be able to assemble it with much more confidence. So mini ASM output unities, not contigs. Unities are unique parts in the assembly graph. One could say that they are high confidence contigs. In contrast, contigs may include regions with ambiguous relation depending on the algorithm used. And therefore, because they use uniques and do not take into account contigs that are doubtful, sometimes the assembly that we get is fragmented. Mini ASM does not build a consistent sequence of their assembly, thus the error rate of the resulting unit is approximately the same as the error rate in raw reads. This is the reference paper for mini map of mini ASM. Again, for sincere students, you must go back and read these papers first to understand the algorithm behind and the mechanism behind how this mapping and assembly is done. So here you are. Now we talk of minimap 2. So here again, search I say minimap 2, and it gives me from the search it gives me two hits. One is minimap, which is what we want to use. So when you click on this minimap 2, it will give us your input menu here. So here we need to define what inputs we want to get. So here again, if you see here, you have first thing is that will you select a reference genome or your history or use built-in index. So here in this case, we'll use a genome from history and build index. So we are doing a de novo assembly, so therefore we're not using a reference. We are using our basic plasmid data set as our initial input, and each read will be aligned to all other reads to generate the first level of alignments and first level of overlaps. Right? Then our single entries, they have been taken from one end, not from the other end. So it is not pair and read. So you know that from data that have it is a single entry, so we select single. And then of course here in this case we go to the collection here. So in the next this one here. So here you are. Will you select your reference genome or from history? From here you use genome from and build index. There is no reference selecting for. Then the data set that you're looking for is plasmid here. So the entry here will be plasmid. Single or paired entry here is single because we know that our plasmid reads are coming one end and not from the other. Single end reads. So from the data that we selected for, then of course select the plasmid data set. So here we again select plasmids, and then select the file for preset option. So here there are preset options for SMRT, for nanopore, and so on. So this is the option that we need to select here. Oxford nanopore, all versus all overlap mapping. This is what we're doing. This is what we give our size and window size, chamber size we're looking for. So these are by default options are given. We can select this option, and then the output file format that you want is what's known as PA. And then you press execute, and the selection and function you'll start having your all versus all alignments. So this is your mini map. This will generate alignments with all reads, all other reads, so as to generate the overlaps that you have between reads. These overlaps will be helpful in basically letting you understand in basically generating your final SM, right? So this is what we do here. I hope people are following, and this is a bit of a lot of input in this minimap 2, but then this is how you go about it. So once you have done this, you press on execute, and this will execute and generate your minimap. So and output, of course, I told you this is to be in the PAF format because this is a format that will be taken up by the mini ASM for its generation of assembly. So therefore, you select for PAF output. So what is the pipeline? Pipeline basically is the input file, the output file of one previous tool is the input file for the other tool or the next tool in the order. So that is what we do here, right? So here you are, and if you and I'm short circuiting the process and taking you finally to the alignments that I get here, and for you it may take some time to do the alignments, but this is what you'll get. You'll get a PA file where you'll have your the read that you're looking for, and then where the other read with which it shows an overlap. This is a 12-column file that you'll have, and Let me show you the details of the columns. So you will have the first column that will be query sequence name, query sequence length, query start coordinates. So this is your start, this is the length of the query. Then start coordinate, the query end coordinate in the region in which the overlap has been found. Then the orientation in which the overlap has been found. Then the query with which the overlap has been found, and in that query again, and the subject in which basically, so this is your target sequence name again here. Then you have target sequence length. So this is your length of the sequence. And then you have your target start coordinate and the end coordinate. So where the overlap was found in the other read that you have here. So this is basically a format, PAF format, that is the tab limited text format, with each line consisting of the above three lines. So these are the built fields that you have. You may have additional fields depending on what some additional information you want to put up here. So then as we go along, you have the maps are ready to be visible in Mini. So next tool, the step 4 here is to, once you get your map reads, you move on to what's known as Mini ASM. Mini ASM is going to assemble the overlap data and give you the final contigs, right? So first you generate the overlap data. Overlap data was important to generate your final assembly. So Mini ASM is now going to look at the overlap data and collate them together to give you the final assembly. So this is still the PA format that we PA output from mini map that you had. This will be the input file, and then you'll have an output file which will be your mini ASM file. So the map reads are ready to be assembled with mini ASM tool. Mini ASM is a very fast overlap layout Dino assembler for noisy long reads. It takes all your read self-mappings, which is generated from Minimap 2 as the input and outputs the assembly graph in the GFA format. So this is what you get from Mini ASM. So final assembly is happening at the Mini ASM stage. Right? The first was to find overlaps by all the comparisons. Based on the overlap that you have, now you're doing your assembly. And that is being done by Mini ASM. Everybody following? Right? I hope everybody is following. Okay. So good. So then we move on and we talk now of Mini ASM and the how to give the input to Mini ASM. So here you are. Basically, this is a Mini ASM input. The tool uses two inputs. One is your plasmid collection that you had your initial files RB01 and RB02 FASTA, and then it takes the input from your the input coming from Minimap 2. So this is the map with Minimap 2 across collection 3. So collection 3 is your RB01, RB02, the plasmid collection, and this is your basically your Minimap 2 output that is taking as input, and then it produces two outputs. You have Mini ASM on data 20 and on data 2 and data 1. So data 1 is RB015 and data 2 is RB025. So the Minimap pipeline is an incredibly memory efficient way of storing data. So Mini ASM and Mini ASM work in tandem with each other. First you do a Minimap 2 for generating overlap data, and that overlap data is fed into Mini ASM for assembly. ASM is for assembly, and that basically brings up the unique or high confidence quantities. Because it ignores some of the low confidence quantities, sometimes the assembly is fragmented, as I told you earlier as well, right? So Mini ASM does not build a consistent sequence of the assembly. Thus, the error rate of the resulting unit is approximately the same as the error rate that you see in raw reads. Then we move on, this is the output that you get from Mini A. So this is GFA format out, and you will have again the unity. So you see 00011, the sequence, and then the information about that unity, and so on. And this is your output of Mini ASM, where you assemble your contigs and high conflicts are being gathered together into a single unit here, right? And then there are a lot of unities that are generated here. Then if you move on and now talk about the next tool in order would be your Minimap 2. So you have to first convert. So what we'll do is, once you've got your unities, we'll do a remapping of overlaps with unities so as to find if there is something that can be improved, right? So first, you know that you had your format. So Galaxy provides you format conversion tools that can convert one type of data to another type of data depending on what is the requirement for the next tool in the pipeline. So here we are doing your conversion, format conversion in step 5. So we are converting the GFA output that we got from mini ASM into the FASTA format output. So we search for again the GFA to FASTA, and we will get the GFA to FASTA here. Click on this, and then it will give you the input options here. So this is your GFA to FASTA input options. Input options, you give your mini SM output as your input here, and then you click on execute again, and this gives you now the faster format for this. So here you are, and you get your GFA to faster for data 23, and you get your GFA to faster for data 24. So this is your initial plasmid sequences that have now been assembled, and now you get a faster file for the assembled sequence. Then we move on, and we do a remapping with Minimap 2. So Minimap 2 takes the faster sequence. So again, this time we are giving as input the GFA faster files that you generated using the output of mini ASM. And you do a remapping to see if you can get a better overlap and refine your assembly. So sometimes you keep doing the steps recursively to improve your assembly here. Your assembly here. One thing that you can do. Then once you're done with this, you can move on check for the. So here is your output again, and now you get your unique data with your mini map that you have rerun here, right? Then what you can also do is, as I told you, mini ASM does not use a consensus model. So there is another tool in Galaxy toolset that you can use for generating a consensus model. That is known as Recon, right? And Recon, again, you search for Recon here, and it will give you a Recon tool here. Click on this, it will give you the input files that are required for the input arguments that are required will be shown here, and then you have to select what the input arguments you want to give. So first of all, the sequences where you give your initial collection of data, that is plasmids, RB01, RB02 files, and then you have your other is basically your map with minimap 2 across collection 3 and collection 25. So your minimap 2 output that you've already redone is being input to Recon now. And then also it requires the third input, that the target sequences where it's going to map here is your GFA to FASTA on collection 22. So you select your FASTA files here, and then you could run this, and this would give you an output here again. And Recon is basically for consensus mode of assembly. So basically, if there are multiple points in a sequence where the sequence has multiple sequences have the same nucleotide, near nucleotide position, it will look for the most frequent nucleotide, and that would be your consensus, and therefore this may be more precise in terms of individual nucleotides. The assembly for long-term pack bio and export nanotechnology typically requires source intensive direction and consensus generation steps to optimize assemblies. And here again, you could use consensus-based assembly. You could use Recon. Then here is what you get as an output of Recon. So you can see these are your uniques, unit 1 here, and then there are several uniques for individual files. So you could look at what is the number of units that is generated for RB01, and what is the number of units that is generated for RB02. So as you can see, optimizing these parameters and which tools to use can be a bit of a complication. So there is one tool that you can use directly, that is known as Unicycler. Unicycler uses several tools and several optimization parameters and does it recursively to generate the best assemblies. So next we'll do a Unicycler-based assembly, right? And before that, what we can also do is we can look for whether our sequences that we've got, the quantities, the final assembly that we've got, how many of these sequences look like plasmids. So for that, you use what is known as bandage image. Bandage image is software that will, based on the property of the uniques or the assembly that you've got, would generate images that would show whether it has partial plasmid character or full plasmid character. So here you are, you could use your bandage image. So you search for bandage and you get your bandage image visualization de novo assembly graphs here. You click on this, and then again the input is only one. This is your mini ASM on collection 19, collection 3. So this is your basically the output of mini ASM that will be taken as an input, and it will generate images for the two different RB01 and RB02 assembled genomes here. So if you look at the output of this here, This is the kind of output that you'll get, and this is for RD01 that I'm showing. Likewise, you'll have an output for RD02. So very clearly, while it shows partial plasmid character, it is a partial circular character. It shows two of the contigs show partial plasmid character, but it is not very clear whether they're actually plasmids or not. So you could refine your model by by altering your parameters or other things, or what you can also do is use a tool that itself optimizes for assembly, and this tool is known as unicycler. So we finally move on to unicycler here. Right? So this is unicycler. Unicycler is basically again, you search for unicycler here. So what I'm trying to show you is there are several different tools that can do the assembly for you. It is up to your choice which tool you want to use. But unicycler is one such tool which has come very recently, and that can basically combine many tools together and do the assembly for you. And as you will see, the assembly by unicycler is highly right. So we'll move on to this now. So here the inputs for unicycler in paired or single data, let's select for none. While know it is a single data, we select for none as the default input in here. And then for selecting long reads, if there are no long, you can leave empty. But we know we have our long reads. We have sequence of nanopore data. So long reads, you select your collection into plasmids. So basically, you're giving your raw files RB01 and RB02 as inputs here. And then we leave everything as default because we will not have time to and of course these options need to be exercised to fine tune the data. We first want to look at the broad picture first. So then we move on and we say execute, and this will generate an image in CAM, right? So this is your unicycler. So unicycler basically would generate your assembled genomes again. So unicycler is a novel semi-global aligner to align long reads to the assembly graph. The assembly tools we used in this tutorial are all implemented in Unicycler. So whatever we have used till now, all are implemented in Unicycler, and the advantage in Unicycler is it will also improvise and use different parameters to see what gives the optimal assembly. So which will repeatedly run these tools on your data using different parameter settings in order to find the optimal assembly. So that is why Unicycler is the preferred tool now, because it can automatically do all the optimization for you to find the best assembly possible. Unicycler tool has a couple of advantages over running the tools separately. First, the modification to help circular replicon assemble. So basically, there are several advantages that you have. Instead of running the tools, you can run it here and optimizes very well for picking up the most optimal assembly. Right? So then we move on and we see so this is the output that you get from Unicycler. For RB01, you'll get four unity, four assembled sequence. I'm showing you sequence one. There are four such here. For RB0, you'll get around 30 such sequences. And when you give this input again to bandage image, now you see of four contigs that you have, one is having a linear nature, more or less, but two of these clearly show a plasmid nature. They are closed circles, as you can see in the image here. And one is very short and has very clearly a linear nature, as per the bandage image that you see here. So now we are confident that our sequence has plasmid sequence, and of course it is showing a circular nature, right? Next, so you can compare the image that you obtained from mini-SM versus what you have in Unicycler. In mini-SM, we had the assembly quality was not so good, and therefore you had partial circular nature. While with Unicycler, where it has used multiple tools and has also optimized the parameters, recursively changing the parameters to obtain the best assembly, you can clearly see that you get at least two sequences that show clearly your plasmid nature and a closed circular DNA format here. Right? So this is the advantage with Unicycler or mini-SM. Then, of course, if you want to now, and remember our original objective was to check for whether these plasmids have the resistance genes or not. So that can be predicted using Abricate, right? And Abricate is again a software that can go back and compare to ResFinder or the resistance finder database and map your synthesis and show what is the similarity that you have with those resistance synthesis, and that will give you an idea of whether your plasmid contains resistance markers. So here in this case, if you see RB01, it has several resistance markers here, and this is the gene name here given, and the resistance against the specific antibiotics is also mentioned here, and this article that was there's more antibiotics in a screenshot couldn't take enough, and some of these are streptomycin, and then you have you have streptomycin again, and you have sulfamethoxazole and trimethoprim and so on and so forth. So this now, because we've done it on RB01, so this now proves that are plasmids that we started with contain resistance markers, and if they spread out, they will be spreading the antimicrobial resistance to other bacteria as well. Right? So this is in brief the hands-on session. Of course, some of you would be doing it yourself, and maybe stuck in some steps because some steps are time-taking. But of course, you will be able to finish it as you move along. You could also have used star MR, which is there in the regular pipeline that is mentioned by the people here, right? So just to summarize the talk now, first of course we talked basically about sequencing techniques, and we specifically talked about long read sequences, and for our purpose of the hands-on session, we used Oxford Nanopore data, so therefore Oxford Nanopore we have done it in a bit of details. Then we talked about the basic galaxy interface. Then we talked how to make a data collection, since all the operations have to be performed on several files. You can plug them together into a single group, and we named it Plasmid. Then of course, moving along, we used Minimap2 to first do all versus all alignment to see where is the overlap. Once we are done with Minimap2, the output of Minimap2 was used by MiniASM to assemble and generate the unities or high confidence quantities, which is a continuous stretch of joint sequence, right? And some of these may be complete sequences, some of these may be partial, and I already told you, MiniASM does not use a consensus sequence and does not take into account the not so confident quantities, so therefore sometimes the assembly may be fragmented. Then we use RAFON, which uses a consensus-based algorithm to generate assemblies. So these basically are doing the same thing with slightly different methods that are utilized here. And then finally, we use Unicycler, which basically uses all these tools together and optimizes them and changes the parameters so as to find the best optimal assembly for you. And as we've seen also, when we look for the bandage image, the output of Unicycler gave you very clearly plasmid sequences, at least 2 of the 4 contigs or plasmid sequences. Others were not so much. So the Unicycler is clearly has an advantage here in assembly. And then we use bandage image, which helps identify whether the sequence is circular or linear. It predicts, basically. It is a prediction, but of course based on certain parameters that it decides. And then of course we use abricate to predict resistance. I'm sorry for the spelling mistake here, RE, right? And that is where we would stop. And thank you very much for your attention. Remember, hands-on is good only when you do it hands-on, right? I had one and a half hour to take you through, so I've taken the screenshots. When you do it yourself, there will be steps where you can get stuck, and there is a good tutorial. I've already given you the link where you can follow and relook, and of course you can always get back to me. Thank you, everyone, and maybe we can have some questions. Right? Not the tough ones.
Thank you, Dr. Vipin, for nicely summarizing the entire process in a very short of time. Yes, you as you said, hands-on means hands-on. And that's why we have created a GitHub channel also, so that the students or the participant can practice on their own, and they can shoot the questions on the GitHub channels even we are not available.
Yes.
Live. So we are lucky to have some questions. I don't know whether they're tough one or they are simpler ones. But the first question is, I will take the first question to a session. So the participant has requested that can you please list out scenarios where to use mini-asm or unicycler, or on what basis, which one has to be decided, or do you always recommend unicycler? So this is a question.
All right. So again, I've already shown you unicycler is the best performance because it would also include other tools. And one of the common ways we go around in predictions is to use a combined evidence approach. Right? Combined evidence approach means you do the same thing two different ways and you unify the result, what is common between them. So that is basically what is preferable, but of course it depends on how you go about it, right? And also depends on what is the data in hand. So, and as you use the tool, you will get familiar with it, and you will also know how to tweak the tool, and then probably you can tweak it the way you want so as to get the most optimized result. But Unicycler, of course, is a good tool.
Thank you, Vipin. So there's another question. What is the main uniqueness of Minimap 2 compared to other available tools for sequence alignment? Can Minimap 2 be used for multiple sequence alignment as well?
So Minimap 2 also, I told you it is basically for all alignments. It is not for MSA. Multiple sequence alignment is you have multiple sequences aligned to each other. What we're doing is actually in Minimap 2, what we're doing is a pairwise alignment. One read versus all other reads. But the comparison is always between one and the second one and the third one and the fourth one. So multiple sequence alignment is not what you can do with Minimap 2. I hope I'm getting it clear. Right?
Yeah, thank you. And I will repeat the answer from Anshu. Also, Anshu also has a text up message here regarding those as per Anshu. And I think Dr. Anshu, because this is a combined session by both of you and me, but we are also left with some of the questions from to you also. So I request all the participants. So this is a combined session. So you can also ask some of the queries you might have in your mind while going through the presentation of Dr. Anshu. And Dr. Anshu, will you please help us in dealing with this QA session? And you can answer your question live.
So,
Right. So, yeah, just to add to what Dr. Vipin was saying about Unicycler, it seems to work with fewer long range reads, and it also has shown to have less misassembly rates. So that is why I was also wanting to add what Vipin was saying in terms of why Unicycler versus other more independent tools, because it actually can.
So Legume Lab is asking, is the ordered workflow only for nanopore? So this is for long read sequences, and depending on if you have smart reads, your input options may be different. Remember, at one place we had especially mentioned that what we have is a nanopore sequencing reads. So those options there you have to select for PacBio if you want to use for PacBio, right? So the order is the same. Only thing is that the input may be slightly different and the parameters will be slightly different for PacBio, for nanopore, or for small read sequence. So that is something that keep in mind. And then somebody has asked when we have short read sequences, which assembler is better to use. So Illumina, I think, gives us inbuilt assembler for use. So if you have short read sequences like Illumina, they will have their own pipeline and they'll have their own assemblers, and that can be used directly, right? And Unicycler basically is if you see Unicycler is basically that can combine long and short reads together to give you a highly precise assembly. The basic function is basically work long reads that give you the context, and short reads that will give you the precision at the nucleotide level, and it combines the two together to give you the final assembly. But in this case, of course, we have only long reads, so we have used Unicycler for long read assembly. These are meant for microbial genomics only. Most probably. Legume lab can be used for eukaryotes. These are meant for short genomes and mostly the prokaryote genomes, microbial genomes. Again, for those of you who have questions, and just I've given the references, you can go back to the original papers and they would answer you most of your queries, right? And that would be, and this would be the hard way of learning, and that is the nicest way of learning also, I guess, right?
Yes, I agree, Dr. Vipin and Anshu. We had some good questions, and I think more questions will come into the mind of the participant when they actually perform the hands-on, and we ensure that we will be available offline or in other channels also, so that if you have any query, we can try to answer them on time, so that you can have a great learning experience during this pre-conference workshop. Okay, and I think we are not having any other questions, so it's time to go towards the end of this session. And on behalf of the entire organizing committee, the INBIX team, CSR East, and all the organizing committee specifically for this pre-conference workshop, and also Galaxy India team, I extend a hearty thanks to Dr. Anshu Bharadwaj and Dr. Vipin Singh for sparing their time. I know these days we are having a great rush of classroom classes, and also the research work and other lab work, and because this is a high time, but still you spare time. I think it's incredible, and it's the commitment you have always shown. And I think we will look forward to you for the another learning experience from you very soon. And for the time being, I again thank you both of you for the great talks you have, the great sessions actually you had. Thank you very much. So Kiran, do you have any announcement to make right now?
Um, no, so that will be now the lunch. So let's say the break right now, and afterwards we join at the 13:30.
Okay, so please join again on time on 13:30. So enjoy your lunch, and I think you will enjoy more after these very great talks. So once again, thanks everyone. So we are just closing the session now. Thank you very much.
Thank you very much. The pleasure is all mine and ours. Thank
Just
you.
one more
So
minute.
I think
Sorry, just one more minute. We want to just take a
yes,
picture.
I just to know. So it's a memory. Please, everyone switch on their camera videos so that we can click the picture here. Prash,
Yeah. Can you see me? Yeah.
yes,
Yeah.
I can see you even with my closed eyes.
Yeah. Yeah. That was a great talk, Anshu and Vipin. Thank you so much. Yeah.
Thank you.
I'll wait one for another 30 seconds till just 5 or 6 got opened, so plenty are not yet opened. Go on, go on. It was a
Yeah,
lunch session, so
please.
you can show your bright faces.
Yeah, yeah, you can delay your lunch, no problem. But this picture is very memorable.
Okay, I will take the screenshot now. 3, 2, 1. Thank you.
And maybe all give a huge round of applause to both these speakers and the INBIX team. Thank you very much. Thank you once again for joining.
Thank you.
Thank you and take care. Bye.
Thank you. Bye. Thank you. Bye.
This is stopped or not? Then now we can close and we can open in only one platform.